Well, good evening, ladies and gentlemen. My name is Eric Priest from St Andrews, and I chair the Rosalind Franklin Award Committee. If you have a smartphone, then you can scan the sticker on your little label, and that'll enable you to access the feedback survey. Or you can get hard copies at the back. So we'd be very grateful if you could fill those in. It will help us in future. And the Royal Society staff will be very happy to help you if you have any questions about that. Now, the Rosalind Franklin Medal is awarded annually to a mid-career researcher to support the promotion of women in STEM, science, technology, engineering, or mathematics. And the criteria are first the excellence of the science that the person is doing, and secondly, the excellence of their proposal for encouraging women. Our winner this year, Professor Nguyễn, meets these criteria brilliantly. She plans to hold a residential summer camp, a very exciting one, mainly for girls, but not solely for girls, who are in year 8 at school, so the same age as her two wonderful children sitting on the front row here. But these will be from underprivileged or minority backgrounds in deprived areas of London. But she is also a world leader on the design and synthesis of magnetic and plasmonic nanomaterials for biomedical applications, and that's what we're going to hear about today. She held a Royal Society University Research Fellowship and then was appointed a full professor of nanomaterials in 2013 at University College London. She's one of the co-founders of the Global Young Academy, and she's also the founder of the Vietnam Young Academy. At the end of the lecture, I shall be presenting her with the medal and the scroll. But it's now a real pleasure for me to invite Professor Nguyễn T. Kim Thanh to deliver her lecture on nanomaterials from bench to bedside.
Good evening. Thank you, Professor Eric Priest, for your kind introduction. And I'm feeling very humble and very privileged to standing here at the Royal Society and to the great audience to talk about my work. But before I go on to talk about my work, I would like to spend some moment to pay tribute to Rosalind Franklin. I did look for the photo of her on the internet, but I couldn't quite find who was the copyright holder. So I went into the Wellcome Library and just fantastically summarized her contribution, and you can read on. And for people who didn't know about her, I think that if you look into the Wellcome Library source, it will be a good one. There are a couple of books written about her already, and it's really moving and interesting to read about her contribution. And so I hope you have read, so I don't have to read it out, the story for you. And if you haven't finished reading it, and this video will be stay live later on, so you can explore about it. And so for me, I feel happy that she's getting recognized more and more, and she for her contribution to the structure of the DNA. So when James Watson Holt needs to be replaced, and Rosalind Franklin name was chosen. And even more that recently on my trip to the Harwell Science and Innovation Science Campus. And I was so happy. I said, I'm going to give the Rosalind Franklin Lecture. And it's like God sent for me to be there to take the photo of the new building, of the new institute named after her. So I'm here today without, this award is to me, but actually it is for my families, my friends, my colleagues, my students, and also my workplace, UCL. So I would like to thank my parents, and especially my mother, and she has been my role model. So she was only few female students who went to the top university in science and technology at her time and study mechanical engineer. And my father, he was a chemist, and during the conversation with his friends, they talked that you have to keep your lecture on time. So I said that, don't worry anybody. I knew that when I was a child that you had to deliver the lecture on time. So I try to do it today as well. So it's more than that. I think I was born during the American War, and we didn't have enough resources. And I'm very particularly now with environmental friendly issue, but I couldn't really throw a white piece of paper away. Because in those times, writing paper not even enough for us, and we had to really, we're very lack of resources, but I'm very lucky to have a parent who really, putting me through education and led me to go wherever I want to go with my career. And obviously, friends is very important. Some crucial for my career, and one of them is Mr. Faraday, who is here. And he was my father's friend, and he could kindly lend me the densitometer for months and months, and probably even over a year, for doing my PhD. So basically, that I didn't have money to buy the equipment, and then you have somebody lending you the equipment to do the PhD. So that was great. And obviously, wonderful colleague, and so I'm very privileged to have a provost, Michael Arthur from UCL, Dean of MAPS, Professor Ivan Parking, Head of Department Physics and Astronomy, Professor Raman Prinjnya, Director of London Centre of Nanotechnology, Professor Andrew Fisher, and in the audience also Professor Artin Donald from Cambridge. So I'm very privileged here today. So I base at the Royal Institution, and unlike any other learned society, Royal Institution is stay in its founding place. It didn't move around. Royal Society actually wasn't here originally, but Royal Institution still there, and as an Albemarle Street. So it is the oldest scientific research laboratory in the world, and there have been 15 Nobel laureates, the highest concentration per meter square. And they discovered there 10 elements, so it's an open museum. You should go down and visit and try your talent of how fast you can play with the music and find out the 10 elements at the Royal Institution. I would like to show a couple of names, and I will repeat their name later on because it's related to my lecture. So Michael Faraday, yeah, okay, so you have a Michael Faraday, and John Tyndall. So Tyndall was the one who discovered the phenomenon of why the sky was blue. And he looked into the light scattered through gas. And so I hope to show you that the Tyndall effect go through the gold we collected from the waste, actually. Here, if you can switch to the other one, you can see the scattering light there, the green one, yes? So that is a Tyndall effect. I need to go back to my lecture note. And then you have like Dewar, because all the thermoflasks were invented by Dewar, And John William stressed is that Rayleigh scattering effect, so I also show some of that effect later on. We work with nanomaterials and we need to characterize them, and at RI, quite uniquely, you have father and sons, both got Nobel Prize. And they make that record, but also that the son made a record that the youngest physicist won the Nobel Prize when he was only 25. No pressure, son. And then I also want to mention about Professor John Merritt Thomas. Later on, in one of the pictures, I will show you what he did for the micro-Faraday sample. And Professor Richard Cutlow is now Foreign Secretary of the Royal Society. And interestingly, that Royal Society had the Foreign Secretary in 1823, many years before the government had their Foreign Secretary in 1782. So Royal Society always forefront in their thinking. So it's really great to be here, and also my colleague Quentin Pankhurst working a lot with the magnetic nanoparticles, so it was really great that I could be working close to him at RI. And so nanomaterials is where is my work focused on in the very small section of nanoscience and technology. So we're using the chemical method and the wet chemical method to make our nanomaterials. But what we need is that some physical understanding to characterize the materials. And then also knowing what physical property we need that fit it back to us for synthesize our materials. We use a lot of biological molecules for our work, both ways. One is that we're using them for synthesis of the nanoparticle. But we can also use our nanoparticle to study biomolecular interaction. And engineer, I never thought that I'm going to do anything with engineer because there was a fighting in the house between science and engineer. And I'm followed being a scientist, but now I'm working with the chemical engineer to design the reactor for the synthesis of the nanoparticle. But also engineer, you have a biomedical engineering, you can building the device, and then with the biomolecular interaction. So the ultimate aim for me, or my research, is that I would like to use the nanoparticle to diagnose and then to treat disease. So I know that many of you are expert in the field, so you can look into the Royal Society FinTrans, a nanoparticle theme issue. I edited it to celebrate 250-year anniversary of the Royal Society. And also, Professor Uta Fried very kindly recommend that I do one of the series, one of the film on the series of the scientific story for the Royal Society to celebrate 350 years of publishing at the Royal Society. So they are all available on YouTube, so you are welcome and free to look at them. Something not quite right. So now I say that I'm going to back with the name I'm listed at the Royal Society. So here is Michael Faraday. And he made this gold salt in 1856, so now 163 years old, and it still exists at the Royal Institution. And I did check it yesterday, so yes, it's still there. And then he beautifully written his work in a note, and it's beautiful, and you can see that the number here, now is a number here, that for him to indexing his lab work. And then they want to publish his notebook, but in order to make money, they call it diary. And later on, he published his paper, is peer review in FinTrans, and I highly recommend any student in the field reading the paper because it's still very relevant today about the effect of the different ionic strength, different type of ligand, and it's still very relevant. So in his original Beckerian lecture, and I just want, it's beautiful to read. He just write the scientific paper. It's almost like he write a poem. So you say that if the solution to be weak, it needs to be weak, and phosphorus needs to be clean because it's a reductant. So part of the gold is reduced in exceedingly fine particle, and you got the ruby color. So you can see that some of that is got a ruby color here today, and we also have some other gold nanoparticle. They look red. And so you can see that if you go to have a red wine, they also have a quite similar color, or the strawberry juice. So the gold nanoparticle have the same optical property. How are we making them? So I, on my UCL lunch hour lecture, the title of the talk was Nanomaterials Tackling the Global Challenges. And if you go into YouTube and you just search my name and nanomaterials, you will find that the way how we make the nanoparticle using lemon on the table there and with the gold salt. And then later on, we look at the stabilization of the gold nanoparticle and effect using egg white. So now here, I'm just showing you very quickly how the gold nanoparticle were made using very simple method, and Turkovic already using this technique using the gold salt and citrate, and again, there's the lemon. So you can see that the gold, first you see that a very pale color, and then you're going to, with time, it get darker, and then you got beautiful ruby fluid of the gold nanoparticle. And that is how the gold nanoparticle look like under transmission electron microscope, because gold got a very high electron dense. So gold is the easiest element for us when you look under the TM. You can make the nanoparticle of the different size, and they have a different optical property. And if you can see that under the UV spectrum, of, let's say, like a solution A, equivalent with 12 nanometer gold nanoparticle. So why gold nanoparticle change from something yellow to red? The reason is that it absorbs light at about 520 nanometer, and that is the green light. So when the green light absorbs, what you have left is the red color. So making gold nanoparticle is easy because, as you can see from the YouTube, we make it during the lecture. We could make it, but how to make it well, that is different matter. Because if you don't make it exactly the same size, they have a different color. They have a different absorption spectrum. And you're mixing up things. So you need to have a really monodispersed one-side particle for your intended application. So in collaboration with the colleague in chemical engineering, we could study with this very classical reaction of gold and silver nanoparticle and study the effect of mass transfer during the synthesis. And it's something achievable at how you're going to start making the different product. I like cooking, and I did do experiment to make something right. And if you don't mix very well, then it gets lumpy and not smooth. So the same thing here, that if you depend on different speed of the mixing, you will have a particle is monodispersed or very polydispersed, that means very different size. So, and now, what is the application? So the gold nanoparticle, we know the typical absorption peak giving you the red color. But when they aggregate, because light have electromagnetic radiation, interact with electron surround the gold nanoparticle, will be different if they are very well apart or they aggregate together. And that's called the aggregation or increase at absorption at a longer wavelength. And why the color change from red to purple? Because when they increase the absorption in the longer wavelength, they absorb the red light. So what it left for the solution is the purple or the blue. So one of the applications we use is the immunoassay. So what is an immunoassay? This assay is the interaction either to identify antibody or antigen. So the antibody is like a letter Y. You've got two binding sites. And that two binding sites going to interact with your antigen. In this case, the antigen is a protein A on the surface of the gold nanoparticle. So you bind this antigen to the protein, and I know to have a bibliometric critic in the audience, but I put the 600 citation there, not to brag, but I'm saying that this assay is very versatile assays, and it's very simple. Why? Because you use your color from naked eye. Your instrument is your own naked eye. The color change from red to blue. So the moment you add antibody in with the two binding sites, they're going to grab the particle. So like you have a game. If I have only one binding site, I only coating my gold particle. I cannot connect to my neighbor. So with this two binding site, that is the key. So they call it monoclonal antibody. You will not see the effect. You need to have a proper antibody. So the more you add, the more aggregate, and you see the more effect, and the color change from red to purple or blue. Normally, you don't use TM to characterize the aggregation because it can be mistaken because of the drying effect. If you dry a lot of solution, it tends to be sediment out, and it can cause the effect like aggregation. But in this case, it definitely is showing that the aggregation of the nanoparticle due to the immunoassay or effect, because we do the control without the antibody, and we don't see the aggregation. So it was fun. I mean, working in the TM lab, it was great because you can see like nanoscale worlds. You see there, and you're zooming in, and you're zooming out, and you zoom out, 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 and you see the beautiful flower. And so the whole flower is about few 10 billions of nanoparticle. It's aggregate overnight. And this was the film that I had to go into the dark room to develop the negative, and then I scanned it on. And unfortunately, in those days, the scanner wasn't that good, and so the resolution wasn't very high. But this is really priceless picture for me. Then you can see that the color of the gold nanoparticle changed from red to the purple. So you can use it very simple assays, and again, I just said about 600 citation, or actually this work, we got a lot of citation as well. Because it's just a simple thing, assay you can do, the color assays, that you can do the UV vis, spectrum, scan them through, and you can see that whether they aggregate or not. And later on, we look into the stabilization of the gold nanoparticle using peptide. And a peptide is a building block of the protein, and you can see act as reminding you of the protein. And one other characteristic of gold nanoparticle I would like to introduce to you is that For 50, this is 100 nanometer. But if you can go down even 40 nanometer of gold nanoparticle, you can see them individually using the microscope because of the Rayleigh scattering. So because you need to have the size of the object larger than the wavelength, but because of the scattering, then you see this single particle. So that's why the name Rayleigh was at the beginning. So now what we do is that we make not even sphere. Well, it's maybe a little bit boring, the shape. So we can go on into the rod shape. And we can make them beautifully with very fine-tuned aspect ratio. And with the fine-tuned aspect ratio, you can tune in the absorption as a longer wavelength. You can see that the original spherical peak is still there at 520, but it gets dampened. Because with the rod, you got light, its electromagnetic radiation interact horizontally and vertically will be different. So that's why you got two peaks. And it depends on the aspect ratio, you can move the position of the peak. And what we're going to use it for, and it's very relevant for what Rosalind had done during her time for finding the structure of the DNA. And what she said is that the phosphate was near to the end because we're using that phosphate backbone characteristic of the DNA for the assay we are developing. So you have a gold nanorod. Very similarly with gold spherical, you got the absorption peak there. But when they get aggregate, you got the increase at a longer wavelength. So when you're adding the DNA got the negative phosphate interact with positive nanorod. It neutralizes the charge. And there is no repulsive charge, and the nanoparticle aggregate. And you see the increase at a longer wavelength. But if you keep adding more DNA, the charge becomes neutral and then become negative. The system becomes stable again because you have a repulsive negative charge. So what we call this is the inverse sensing or inverse sensitivity. Actually, at a lower concentration, you can have a higher detection. You can detect it better. We also look at the different extracellular DNA in the environment using the same assays. But for many different kinds of disease, what we are looking at is not a very short DNAs because the previous assay we developed is based on the short DNA. So if we need to study the binding between the long DNA, then we need to have some different assays. So this is the assay where we're using the gold nanorod and the piece of the DNA, the long DNA, and they act like open chromatin. And because the open chromatin interact with the receptor, in this one is a transcription factor, and you can study their interaction. So you can use this gold nanorod for that interaction. We can also use the gold nanosphere. So this work was inspired by Professor Ivan Parking because his group was pioneer in looking the interaction of small gold nanoparticle interact with photosynthesizer and then to kill the bacteria. But because we work with rod and we want to see that how can we use rod to use the same effect? And it turned out that it works because in order to make it work, we need to make the rod short and fat because then we can move the absorption to the shorter wavelength so that the overlap with the crystal violet so that you can have a plasmonic coupling to produce ROS. It's a reactive oxygen species, and that ROS is the one to kill the bacteria. We also look at the gold nanostar, and the difference with gold nanorod and gold nanostar is that the electrical concentration around the tip of the rod and along the side of the rod will be different with the electrical field concentration at the tip of the star and along the spike. So we could now look into better effect with the star compared with the rod. And now I'm moving on to the different topic, is that the Michael Faraday work into the magnetism. So as you know that he is the one to discover the magnetic induction, but also that the magneto-optical effect. So in here, you can see that his original apparatus, magneto-optical apparatus, and he put the dense glass on top, and you put the electric current through, and then shine the light through the dense glass, and then the electrical current and the magnetic field induce and changing the light. So that is an optical magneto effect Michael Faraday discovered in 1845. So it's relevant to very the end of the work where we are not going to say the effect. We're talking about the optical effect of plasmonic nanoparticle, but later on, if you can exploit the optical effect of the magnetic nanoparticle as well. So I edited 2 books on magnetic nanoparticle. The field are really booming, and I couldn't help it because I would like, they said that you're crazy, that's why you are editing the book so frequent. But I said, well, you know, there was lots of things going on, and I didn't want to miss it, and so I'm ending up editing it quite quickly after the first book, and you can see that there is so many different application of the magnetic nanoparticle. I'm just going to give you the most recent, which I found at the clinicaltrial.gov, is that people use iron oxide nanoparticle as the MRI contrast agents, and the drug they're using is that ferromoxitol. So ferromoxitol, it is approved to inject into the body for anemia. So you can see that the iron oxide nanoparticle is really going to already have a type treatment. Other application is that the magnetic targeted drug delivery. So this 3-year-old girl, she tried her best to deliver the magnetic nanoparticle from the knee to the thigh through the giant blood vessel. And it's a challenge because this is not static. There was a trick, there was a pump there, it was engineered. Okay, so I think somebody, or Quentin in the audience, were laughing. So there was a pump to mimic the blood flow. So then, if you think about the targeted drug delivery, it is a challenge. If you think that you can move the magnetic particle from the knee to the thigh because you will have a blood flow, and that's something you need to overcome with. And your blood is also very viscous. So there will be a lot of challenging, but this is the field that people are actively working on. So now, I would like you to have a little bit of fun with the magnetic nanoparticle, but there is a word of caution, health and safety. Number 1, do not open, eat, and drink. Number 2, do not keep two magnets close together because you will have the very strong attractive force, either going to hurt your finger or hurt nanoparticle because they doesn't like to get out into the floor. So please remember 2 things, and then now we're going to hand it out for you, and we're going to have a little movie for you to look at. To have my lecture finished on time. So when you finish it, can we have it back? Because we're going to use it for the residential summer camp for the children. So if anybody haven't got a chance to play, you are stay on. We have a stronger magnet for you to play and seeing the effect. So when we make the magnetic nanoparticle, you know now there are 2 elements there. There is a magnet, that means the external field, and your nanomaterials, nanoparticle. So you want that your nanoparticle have to have a response to the magnetic field as much as possible. So that we call it saturation magnetization. That is very characteristic of the materials. So let's say that I compete with you and making the nanomaterials, you have to compare the saturation magnetization because it's standardized per unit mass. So you naturally, you want to make the strongest one possible, but there are challenges. Because the pure ion have a very negative standard reduction potential. That means that this ion will get oxidized very easily compared to gold nanoparticle. So 3,300 years ago, Tutankhamun mask is still bright of gold, but no way it can keep anything that's of iron for that long. So then we can also have a different kind of alloy in between, okay? So when I starting my research in magnetic materials, I want something like, when you're young, you're a little bit more ambitious. And they say, okay, go and get something the most magnetic. iron was too difficult. I knew that. So I just tried to say that why it's so difficult, because it oxidizes so easily. So I wanted to do a little firework because the Guy Fawkes Night is coming. But unfortunately, I couldn't really get it over the airplane. And then it's also difficult because if you go to the Euro channel, it's too tight and they don't transport it. So you can go through the sea, but they say that if you pay for 3 meter by 3 meter container, only keeping your zero valent gold nanoparticle, then we can ship it for you. But by the way, it's too expensive, we're not going to do it. I said, okay, what about that we drive on the way to the Continental in Czech Republic by car and coming back? And they said, no, you need to have all of this health and safety paperwork. So now I don't have the firework for you in real, so I need to play this video. I need to click into it. It did work before. That's the only thing. I really want to show this video. Yeah, but I need to click on it. Okay. Okay, because this took over my my screen. Wow. So you can see that the iron, zero valent iron, will burst into the flame. So it was too difficult for me to make the iron. So we made cobalt nanoparticle. I could make beautiful cobalt nanoparticle, but it's inorganic solvent, so it was not really useful. Then we make them in peptide and disperse them in the water. But later on, it looked, 2 days later, it turned into emerald blue. Very beautiful, but totally useless. Because you change from the ferromagnetic into the antiferromagnetic stage of the nanoparticle, and you lost the magnetic property entirely. So we try to make the different kind of alloy because they also have a high saturation magnetization. And you can see that you can make the spherical, you can make the cubic shape, and that octapod shape because you've got like 8 legs, and then bilobar, and you make them star, rod, or tetrahedral structure, and also you can make Y, different kind of tetrapod as well. Then we need to do the characterization, and we use X-rays, and so that's, remember that the name I put at the beginning, that 2 bracts, they get Nobel Prize for analysis of the materials using the X-ray. So that is the XRD, or X-ray diffraction patterns. You need to characterize them. So basically, you have a reference, and then you can see that your particle of weak composition. But also, the width of the peak allow you to calculate the size of the particle. So also, by the TM, you can determine the size of the particle, but XRD, the 2 different is that XRD allow you to do a lot more sample than the TM, where you can only look at a few hundred particles at the same time. We also use high-resolution transmission electron microscope to look at the particle, because you can see that here the different atoms. So by seeing the distance between the crystal lattice, you can determine of what phase of the particle. So our aim is to make very monodispersed particle, and we could. But importantly is that what's the chemical composition? So this is a cobalt ferrite, and we can also make a very beautiful octapod shape. And I'm just giving you a little bit a flavor of the challenge of what we are working with. So you can have a different solvent, octene ether or octadecene, that basically different solvent. You can see that you have a different joules of particle. So you can use a different kind of reductant. So like hexa decanediol, or you have octadecanol. So they're different reductant. You're going to have a different kind of reaction. You have a different kind of nanoparticle. But also, you look at the reaction time. It depends on the reaction time, and also it depends on the different amount you are adding in. So you can see that we are busy. Many of us working in the lab and making different things because there is so many different parameters that we need to look at. And knowing the physical property we require, we go back to chemistry and finding the nanoparticle, what we want. So if you remember that on the table, that the alloy iron cobalt got very high saturation magnetization, 235 EMU per gram. So we aim for that. But we need to have a coating, and this coating is platinum, because platinum is inert, a bit like gold. And then we need to disperse those nanoparticles. Then we didn't give up the aim of making iron. Remember that the iron zero valent is so difficult. It bursts into the flame. So the way how we made them, that we know that we couldn't make the pure iron, but what about we got a little bit layer of the iron oxide. And it turned out that when it reached 4 nanometers, it doesn't get oxidized any further. So the key is now you make a whole thing bigger, then you get a bigger core, and you're going to have a bigger magnetic moment of your nanoparticle. So that shows you a little bit about characterization, because there are physicists working on magnetism today. So I just show in that here's the saturation magnetization, the MH curve. That's where we characterize the magnetic property of the materials. So we found that our iron coated with oxide nanoparticle is very good in heating compared with commercial available nanoparticle. Our value get into 3.6 compared with all of those commercially available nanoparticle when you make this zero valent iron coating with the iron oxide. So the aim is that I still want to make the coating with gold nanoparticle. This is the work where we try coating with cobalt and also iron oxide. So then that is one direction. The other one is that I bring back this table again, is the iron oxide, okay? So the iron oxide have a lower saturation magnetization, but it's FDA approved because it's the clinical trial, you can see that they use for injection into the body. So we look into that, how to make the gold nanoparticle using the iron oxide. It's remarkable that in 1852, Mr. Jean Lefort already know that the composition of 2 types of oxide, he called it ferrous and ferric oxide combination. And interestingly, this is his original paper where he need to, they call it like sectional weekly report to the Academy of Science. Very similar time with Michael Faraday, and he also carried lecture at the Royal Society. And remarkable in here, he said that if somebody reads French, that the oxides, these oxides are black, and they attract to the magnet. So already in those times, we already know that using the base and the iron salt, you could form the iron oxide, what we know now, that the magnetized nanoparticle. So and let's show you the charge. So that in 1852, and then not until 1938, where Elmore looked into the colloidal ferromagnetic nanoparticle. That is different thing. So the colloidal is that where you have a very small particulate dispersed into the water, not in the solution, whether water or some other solvent. But again, not until 1981, where this is the first paper talking about forming of the nano iron oxide nanoparticle by René Massard. So actually, in iron oxide nanoparticle, compared with original Michael Faraday work, is 125 years later. So I will show you, Mark is going to do a very quick demonstration of how the iron oxide nanoparticle are forming. So you have two salt. By the way, this is, we call it giant spoon, because one of the postdocs, he liked to brew beer. And he recommended us to go to the shop to buy that for he brewing beer for our reaction. So here is the iron 3 salt, got yellow color. Iron 2 salt got a little bit kind of, like green color, but when it gets oxidized, they will change the color. Sodium carbonate is baking soda. Kitchen team. So you mix two of them into this iron solution, mixed of them, and you dissolve them in water, you have sodium carbonate. So Mark that put the mixture of 2 iron salts, and now seeing, I would like to have a camera zooming in, please. Yes. So now he pouring in the sodium carbonate, and you can see that the gas coming out, and it turned black. So you form the nanoparticle immediately. So is that all simple? Yes. But as I said before on one of the slides, I'm giving you all the ingredient, but do you know what the concentration? Do you know what the volume? And do you know what to do? I mean, you're mixing two things, but all of these nanoparticles will have a different size and different population. It depends on how you're going to do that. Previously, I already mentioned about mixing. So it depends how Mark mixed today or he mixed tomorrow. You will have a different kind of nanoparticle. So that is a challenge we're going to have. So now we're going to have this one ready, and we're going to giving you one demonstration of something previously made of the gold nanoparticle. So as you can see, it's on sediment out, but you can now use a strong magnet. Where's the strong magnet? Yeah. So I'm going to see if I can make a volcano. So magic, because I got a magnet here. And the nanoparticle inside, they are magnetic and they are black. So this is not the difference with what we already knew by Lefort work in 1852. I would like to have a slide back. But the more recent work from our group is that we look into the shape and the structure change of the iron oxide nanoparticle forming using the sodium carbonate. And by the way, if somebody say to you that cyan outreach is useless, actually this work come out from my Royal Society summer exhibition. Because we didn't want to bring sodium hydroxide to the public at the South Bank, so I was thinking, why we try the sodium carbonate, because it's a cooking ingredient and it's milder. Then Christina, later on, looking at the evolution of the different shape of the different structure, and then the face, because iron oxide have many faces, and she identified some immediate face. So following on with that work, we look in the iron oxide in the microfluidic reactor, and this is in the collaboration with Max Bessenhardt in the audience, Alec Lagro now in Italy, and Professor Asiros, Gabriel Levis. So what it is that now, to stay away from all the variable, which is very hard to control, how we can now to do the reaction in the millifluidic or microfluidic reactor, because you have a pump, so they can control the flow rate, you can control the residence time, you can control the temperature, you can control the addition, and you can control the mixing. So all of different things you could control with the microfluidic reactor. But one thing that nobody could do really before is that to look at the mechanistic formation of the nanoparticle. So we shine a very strong synchrotron X-ray through the reactor and look at the reaction. And what it turned out that we knew, but we could not really figure out the mechanism of the different intermediate forming the nanoparticle. What you want is that the black magnetite, because it's very magnetic. You don't want any intermediate like the iron carbonate, the green, plate green in between. So you need to be able to control your reaction to minimize the intermediate so that your reaction will be 100% if you can. That forming only magnetite, not any other intermediate. That is why for seen mass-that reaction for many, many years, and it's still challenge in the field that to find the iron oxide nanoparticle with very regular shape, that monodispersity, and also the magnetic property. If you look into the magnetic property, you can see like variation hugely. So with this work, then we can also look, we look through the TM of the different time, and then see the evolution from 0 to 10 minutes, and we can see that in a couple of minutes, we could form the different phase, so we can monitor the reaction. But the trick for my demonstration was that the kettle already pre-boiled. So you got 100 degrees, it's very hot, and you put into the reaction, so it reacts immediately. In this case, the reaction we use at a lower the temperature. So whatever you're going to make your nanoparticle, that is not the end of the story. You can have your nanoparticle here. You have only sodium carbonate. To make it to have a useful application, you need to have a ligand. That's something else on top of it. You don't want them to aggregate, because we know gold nanoparticle, gold nanorod, when they aggregate, they change the optical property. Later on, I will show you the slide. When the magnetic nanoparticle, when they aggregate, they also change their magnetic property. So you need to be able to functionalize them. It's a different kind of molecule. And that molecule then have a specific binding to the intended application, okay? So one of the application is that we would like to have the magnet that we can pull, the one we want to pull. So Yeah, so like it's a magnetic separation. So I'm just going to see that whether you can use this particle capture the bacteria. And one other application is that you can now, the magnetic hyperthermia that we're using alternating magnetic field, and then you can heat up the nanoparticle inside the body, and you can release the drug, and then we can also look at the release profile of the particle. And then here, where we say that the different magnetic nanoparticles have a different property because you can see that they have a different heating property when they aggregate. And then I said about the microfluidic reactor already, and now I just want to say the final thing about what the future holds is that you the combination of the magnetic and photohyperthermia. And the Rosalind Franklin project, why we chose the GCSE level, because if the student choosing the triple science, they're more likely to do the science. So we have a team of very talented outreach expert in the to run the science camp. So Professor Raman Prija already got the APS prize for his children's book, and Martin did the Royal Society Summer Exhibition. So the children will be having fun in the camp and also learn the science. And this is the group as the basement of the Royal Institution. And the break table, we were privileged when we had an office and to have a table to use. So the work has been very collaborative research and very international efforts. And I would like to thank for the team and many people for the live experiment and also for the contribution of people with the Rosalind Franklin project. And would like to thank all the funder. And that is only for the expert. If you like to edit a book, then please contact the Royal Society. And with that, I would like to thank you for your attention.
Well, thank you so much for your fascinating lecture, which clearly is giving us insights into many really important advances that are going to take place of relevance to medical physics in future. Unfortunately, time has gone on, so we don't have time for questions, but feel free to come up at the end of the lecture and ask her individually if you have any burning questions. It's also really impressive to me just what a fantastic role model you are for young women coming into science. This is a really important aspect of your work, which we admire very greatly. And so I'd like to present you with the, just a bit of magic there, present you with the 2019 Rosalind Franklin Medal.
Thank you very much.
Well done.